All right. How is everyone? 9 people. Wow. Let me open the text.
Before it grows to 16,
Yeah.
space of 30 seconds.
Mm-hmm. I'm good. Thank you. Just bringing up my lecture notes. I actually have lecture notes now. After like years of teaching this course, I've started like planning my lectures ahead of time. Go over the difference between greater than and double greater than. Sure. All right. I don't make a big distinction between these in what we do here. But here's the main thing you're going to see. You'll sometimes see, P arrow Q, which says, if P, then Q. And you'll sometimes see, like something P, comma, Q, comma, R, double arrow S. And I would take this to mean as if P and Q and R, then S. Which would be exactly the same thing as P and Q and R implies S. It's the same thing. But in the text, right, the things that you're asked to prove are usually written in this form. Just to make it clear that these are the hypotheses. Otherwise, you kind of go nuts with parentheses, right? If we wanted to show that, P and Q and P implies Q, we could say P and Q, comma, P implies Q. And the implication with the double arrow basically says the things on the left taken together imply the thing on the right. We could write this without the double arrow by saying, P and Q and P implies Q. So it's just a shorthand way of representing that. Let's see, is there a typo on 3.5.2a? Let me see what 3.5.2a looks like. 3.52a. Prove with truth tables Q and not Q implies P. That is correctly stated. So the comma means that given the hypotheses Q and not Q, we can conclude P must follow. So in our other way of writing theorems, here's what that theorem says. P, not P, Q. That's a weird one. What's a good way to think about that without just giving it away? Well, they said Q, not cube. I said P, not P. But same idea. But let's just truth table it. Okay, I'll switch this to match what the book's doing. Q, not Q, implies P. Well, here's Q. Here's not Q. Let's do Q and not Q. So Q could be false or true, not Q is true or false. Q and not Q is false in both cases. And so Q and not Q implies P. Well, look at the implication table. So we're looking at values for x and p, and we're looking at the value of if x then p. So if x is true and p is true, this is true. If x is false, this is always true. If the hypothesis is true and the conclusion is false, this is false. So to fill in this truth table, we're looking at a column where we have, x implies p, where x is always false. It doesn't matter what the value of p is. This implication is always true. Now that's weird. This is saying Q and not Q implies I am a rock star, right? And that is a true theorem, right? Absolutely 100% correct from the standpoint of propositional logic. If you can prove that Q and not Q are both true, then I am, the Queen of England. It's that false implies anything business that keeps popping up. And yeah, it's disturbing. Strange at best. Maybe that's what's wrong with the universe, I don't know. All right, other questions. Next questions.
Chat, chat.
Excuse me?
Chat, chat.
Chat, chat. Could you put that back on the screen for a second? Yeah. There we go. Yep, you're welcome. All right, so we all right, well, Friday's your last best chance for homework questions then. So keep working on the homework and bring questions Friday. So we talked about proofs on Monday, and we went through some proofs. We did some direct proofs and some indirect proofs by contradiction. And then we finished by talking about even and odd numbers, and I said we'd do some examples of proofs today that relate to even and odd numbers, and these are classic sources for questions on exams and homeworks and things like that. So they're representative of proofs in general, but these particular kinds of questions come up fairly often on tests. And give us a bit of a nice entryway into number theory for our next topic. So let's talk about evens and odds and proofs related to them. So let me start with the definitions we did last time. So an integer n is even if there exists some integer k such that n equals 2 times k. And an integer m is odd if there exists some integer j such that m equals 2 times j plus 1. So we're familiar with even and odd numbers, right? 2, 4, 6, 8, 10 are the evens, 1, 3, 5, 7, 9 are odds. So here's a way to formalize that concept. An even integer is twice some other integer. An odd integer is not twice another integer. It's actually one more than twice some integer, which means it's one more than an even number. And there's other ways we could have defined this, but this is a working definition for what it means to be even or odd. And we're going to stick to integers for most of today, so I may not keep saying, you know, in the set of integers, in the set of integers, but if I don't say, let's just assume we're talking about integers from now on. And so we can start to make some statements about evens and odds, and we can try to prove these statements using, you know, some of this rigor of propositional logic. So here's a theorem. If n is even, then 5 times n is also even. So if you start with an even number like 2 and you multiply by 5, you get another even number. 16 times 5 is 80. That's also even, just like 16. And we would like to prove this. So let's write out a proof in a fair bit of formalism. We're trying to prove if P then Q. We can't really do anything unless we know something about the hypothesis P. So I'm going to start off with the first step of my proof being the one thing I know, which is the hypothesis. So my proposition 1, n is even. The reason for that, that's the hypothesis. Someone said in chat, even plus even is always even, but we'd have to prove that, and we will prove that. And then we could add even to itself 5 times, and we'd be done. Cool. All right, so statement 1, n is even. That's true because that's the hypothesis we're given. We need to go blah, 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 blah. Bingo, 5 times n is even, QED. So we got to fill in that blah, blah, blah part. All right, just about any time that you have a proof involving even and odd numbers, you're going to want to use these definitions of even and odd. Because these definitions get us to, you know, arithmetic expressions, and we can start doing things with arithmetic expressions. The word EVEN or ODD, we don't have a whole lot of algebra that works with that. So in this case, I've got one proposition, n is even. My second statement is simply going to use the definition. And I'm going to say there exists some number k in the integers such that n equals 2 times k. And my reason for that is definition of even. Now I used a k up here in the definition. If I wanted to use j or w or elephant or something else, I can put a different variable in here. Right? This definition of even is that there is an integer such that n equals twice that integer. If you're already using k for something else in your proof, you know, I would write my definition, there exists an I in the integer such that n equals 2 times I. Right? So, so feel free to change that variable. That's going to be really important in a bit. Alright, I've got two propositions. I can do anything I want as long as it follows logically from these two propositions, or from something that I know. So this is where we get into this kind of like puzzle playing game, right? So I'm going to get a separate sheet of paper, and I'm going to say ignore this. If I'm actually putting this on my test, I'm going to mark this as a section which says, don't pay attention to this. This is where I'm thinking out loud. And so what am I going to do down here? I'm going to look at where I'm trying to get to. I'm trying to get to the fact that 5n is also even. Which means I want to show 5n equals 2 times some integer. I'm not going to say k because I'm already using k in here, but I want to show there exists an I in the integers such that 5n equals 2 times I. Alright, I'm trying to find some way to write a statement that will show 5n is equal to twice an integer. Any ideas how I can get from what I've written so far to showing that 5n is 2 times some integer? And I've already got n. Yeah, go ahead.
A clarifying question. Are you trying to find an I such that if you use the same value of I for n, that both sides are the same, or?
I'm trying to find a way to convince someone that I can write 5 times n as 2 times an integer. Right? I want to do something to say, hey, this can be written like that. So in some sense I'm looking for an I so that 5n will be 2i and I will be an integer. Don't tease me by saying it's snowing outside. That was nice last night when we got snow.
Yeah, I know. It was just a suggestion for a proposition.
Oh, cool, cool, yeah. All right, so let me offer a suggestion. If we don't know how to do something, just start doing something anyway. Right? This is the nature of mathematics. This is the nature of computer science. Just start doing something. It's engineering, right? I want to make a statement about 5n. I have no idea how to get there. But I do know something about n. I know that I can write n as 2 times k. Let's just multiply n by 5. And I might do this on my ignore me section, right? Or I might do this proof and then rewrite it and skip the unnecessary steps. But I know that n is equal to 2 times k. What if I just multiply by 5? I know 5n is equal to 10 times k. Well, 10 times k is 2 times 5k. And if k is an integer, we can believe that 5 times k is also an integer. So I'm not going to require you to prove facts about integers, like adding 2 integers gives you an integer, or multiplying 2 integers gives you an integer. We'll take that as given. But what I've done here is I've shown that 5 times n can be written as 2 times an integer. And that's what I'm trying to do. So now I'm going to add this to my proof. I'm going to say 5 times n equals 5 times 2k equals 2 times 5k. And that's going to be algebra applied to what I had in proposition 2. And that's all I need to do. Now for my fourth proposition, I can simply say 5n is even.
You wouldn't have to do anything to switch the 2 and the 5.
I did. So that's a commutative rule of multiplication, but we don't need to spell that out in these kinds of proofs. We can use properties of integers like 2 times 5 equals 5 times 2. But you're right, there is a step in there, which is commutivity. So now I can write 5 times n is even. That's the definition of even combined with the fact that 5 times k is an integer, which again we can take that as, you know, a property of integers and multiplication, that 5 times an int gives us an int. So this is a complete proof. Yes, you need to state that 5k is an int. Thanks. So starting with n is even, we've shown that 5n is even. And that's what we were trying to show. So that's where we can say QED. All right, at some level this is really simple. At some level it's kind of confusing, right? The simple part is, you know, all we did was multiply by 5 and switch these around. The confusing part is why this turns this into an acceptable proof. And there's lots of stuff going on underneath there, lots of machinery. All right, so that's a good proof. Let's do what someone said in chat a little while ago. Let's show that the sum of two evens is even. So here's a theorem. If A and B are both even, then A plus B is even. All right, so what should we start with? What's a good first step for this proof? Someone said even equals 2 times k, define k. K is contained in the integers. Same idea, 2k plus 2k equals 4k, and 4k is 2 times 2k. Good. So in chat, I'm seeing some good material for this ignore section, right? Figuring out why we think this is true. And this is generally how you want to start doing proofs like this, is convince yourself that it's true. Try to figure out, you know, well, if I take two evens, why is the sum going to be even? Or try to convince yourself that it's not true. Try to find something that breaks this and see what you keep running into. All right, so I'm seeing that, and then somebody posted A is even. So that's going to be my first proposition. Again, I'm going to start with the hypotheses. So proposition 1, A is even, and that's a hypothesis. And now I can go ahead and do some of this, you know, A equals 2 times k, where k is in the set of integers, and that's the definition of even. Or I could have said there exists a k in z such that A equals 2 times k. All right, what's step 3? B is even. Good. All right, be careful with step 4. because somebody said 2 times I. So I'm going to say B can be written as 2 times I, where I is an integer. And that's also the definition of even. And the important thing here, I do not want to say B equals 2 times K. Because I've already used K. I've set K equal to half of A. If I say B equals 2 times K, I'm now stating that B is equal to A. And that's not a proposition. That's generally not going to be true. So be really careful about that, right? It's a small conceptual error, but it can compound and lead to a wildly incorrect proof. So I'm going to pick a different I here, right? And I'll put a note here. Putting comments in my proof, how cool is that? B is not equal to 2 times K, so we don't want to write that. All right, good. We are off and rolling. What could we do now? There we go, A plus B. And this is just algebra. I could have written 1 plus 1 equals 2, and that's still part of a valid proof. It may not be a useful step, but I can write anything in here that is true, and my proof still continues to be valid. And without knowing anything about A and B, other than that they're integers, right? If A plus B is equal to 2k plus 2I, I can write that that's also equal to 2 times k plus I. That's just algebra. Nothing to do with evens or odds or anything else. So since I've got extra space on my paper and I like drawing Greek letters and fancy Z's, I might write the following. K plus I is an integer. And the reason for that, properties of int. And k is an integer from step 2, and I is an integer from step 4. So yeah, so algebra, we could mention that we use steps 2 and 4. And if you're going to err on one side or the other, I would err on putting too much detail in here at first, right? And then I might say, okay, you can back down a little bit. But you don't want to make the mistake of not explaining your reasons for each step. Because if you skip a few steps, right, and you try to write down the reason, you'll realize that this does not follow immediately from what you've written so far. There's something else you did in your head, right? And that'll help keep you honest about it. All right, so A plus B is 2 times k plus I. K plus I is an integer, and so A plus B is even. And this is the definition of even combined with step 6. And that's what we were trying to show. Alright, let me offer you a taste of things to come. So this is one of these pay attention moments, because this is something that's going to come up a lot in multiple courses. We've just shown that an even plus an even is an even. And in chat a little while ago, when we were trying to show that 5 times an even is even, someone said, since an even plus an even is even, adding 3 evens is even, adding 4, adding 5 would be even, and that's what 5n is. So let me ask you this, and I want you to think about this. And I'll be a little sloppy here. I'll just say even plus even equals even. Don't write that down as part of a proof or something, right? The way to write this would be, you know, if I and j are even integers, then their sum is even. But I'm going to be a little sloppy for the next minute. So we know an even plus an even is even. What can we say about adding three evens? Even plus even plus even equals even. Can we prove that by using this?
Just say the answer to the line above is the same as that plus another e.
Okay, so we could so let's go a little formal. Okay, so suppose we've got a bunch of even integers, n1, n2, n3, n4, and so on, right? We know that n1 plus n2 is even, right? And we know that because we've got a theorem that adding two evens gives us an even. Suppose we look at n1 plus n2 plus n3. We can write that as this, n1 plus n2 plus n3, addition is associative. And this thing we know is even, because we just showed that. And this thing is even, because we were given that in the hypothesis. And we know an even plus an even is even. So we've proven the sum of three things is even. But what can we say about the sum of four evens? Anything?
Double n1 plus n2, which is n1 plus n2 added with itself, essentially.
Okay, so let me do it slightly differently. Let me do this. Let me write this as n1 plus n2 plus n3, all of that plus n4. And we just proved 60 seconds ago that the sum of n1 through n3 is even. And we know that n4 is even. And so this sum is the sum of two evens, and so this is even. So by knowing that two evens add up to an even, we were able to show that three evens add up to an even, and four evens add up to an even. Could we repeat this one more time to show the sum of five even numbers is an even number? Absolutely. Could we repeat this 100 times to show that the sum of 100 evens is equal to an even number? Absolutely.
Sounds like a situation where a series or a sequence definition would come in handy.
It would. Because suppose I give you a question on a test, prove that the sum of 1,000,000 even numbers is an even number. You could do this approach, but it would take you, 1,000,000 sections on your paper to get all the way up to 1,000,000 even numbers being added together. But we understand logically that there's no reason we couldn't do that other than time and the amount of paper we have. But we use this to go from 2 to 3 to 4. We should be able to go up to 4,000,000 if we wanted. But this does not prove that adding 4,000,000 even numbers gets us an even number. But the process of going from 2 to 3 to 4, we know in our heads that we could generalize that. but we still need some machinery to be able to prove that you can actually do this for, you know, a million or a billion or a zillion even numbers. So we will learn a way to do that in a few weeks. It's going to be something called mathematical induction. And it's the punchline of the whole course. And it's an essential punchline for CSE222 and 223. So this is a preview of what we're coming back to later on. So just let that kick around in your brains. And yes, exactly, right? So we could do this by saying dot dot dot, right? But dot 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 is not formal. Mathematical induction is just the formal version of dot dot dot. It's the formal way of saying, and keep doing this until you get to the answer. And it's a beautiful tool, and it will open up all kinds of possibilities for us. And yeah, that's a good generalization of the ith step. And that underscore is a subscript if you're using LaTeX, which is even better. All right, so let's look at some more proofs involving these things. So let me give you another theorem. If A plus B is odd, then either A is odd or B is odd. If the sum of two integers is odd, then the first one is odd or the second one is odd. And we'd like to prove this. So let's start off with A is odd. That's a hypothesis. There exists a K such that A equals 2K plus 1. That's the definition of odd. I'll write down that, nope, I'm off in nowhere land. A plus B is odd. That's the hypothesis. Step 2, there exists a K such that A plus B equals 2K plus 1. That's the definition of odd. All right, so my question is, what's our third step here? We've stated truthfully that A plus B is one more than twice an integer. We need to go from there to somehow showing that either A is one more than twice an integer or B is one more than twice an integer. And you can think about this for a minute, but it's not clear that there's a good next step to take. This is a slippery thing. Go ahead.
Is using a modulus operator an option here?
This is not an option for this part of the course. It will be in another couple of days.
Darn it.
Yeah. All right, could we do an indirect proof maybe? Yeah, so somebody said we can't let one of the values be odd, question mark. We don't know that one of the values is odd. That's what we're trying to show. And if we write down, you know, A is odd, our proof falls apart. Because unless we have something up here that justifies that, we've written a statement that we don't know is true. And everything that follows is contingent on that statement being true. And if we eventually show A is odd, all we've shown is if A is odd, then A is odd. So this is a question that works really well with an indirect proof. So instead of arguing it like this, let's take a totally different approach. And so let's do a proof, which is indirect. Okay, so statement 1, A plus B is odd. That's a hypothesis. An indirect proof, what we do is we negate the conclusion, and we argue to a contradiction. So step 2, negation, A is odd, or B is odd. The reason for that, that's the negation of the conclusion. All right, really important that you negate things correctly. This is a easy place to fall off. So let's use De Morgan. We have two things. We're taking the disjunction, the or of them, and we're negating that. So let's write an equivalent version of statement 2 using De Morgan's theorem. So not this or that is the same thing as not A is odd, and not B is odd. That's De Morgan's theorem applied to step 2. Okay, I didn't explicitly state this when we described even and odd, but it follows from this. Every integer is either even or odd. That would take a lot of work to prove, but we'll take that as a fact of integers. Every integer is either even or odd. So if A is not odd, A is even. And if B is not odd, B is even. And I'll just say properties of integers. Well, if A is even and B is even, what do we know? A plus B is even. So this was theorem, 42. And so the reason for this is, theorem 42. Or prove this. So if you see this on a test, right, and we haven't already, in a previous part of the same question proven this, you would need to actually do a proof now that A plus B is even. So A is even, so A is 2 times K, and B is even, so that's 2 times J, and A plus B is 2 times K plus J, which makes that an even number. But in the interest of time, I'm just going to refer to, this thing that we already did, which I'm calling theorem 42, and, but we know we could prove that.
If such a situation came up on a test, would it be better to prove that that A plus B is even on the same sheet of paper, just indent the 1, 2, 3, 4, etc. for...
I would just continue it, right? Instead of writing this, A is even and B is even, I would go ahead, step 5, A is 2 times K. Step 6, B is 2 times J. Step 7, A plus B is this. Step 8, A plus B is even. And you could, I don't know, put a little dotted line or something. You could indent it if you wanted, but I would definitely, just keep continuing it, numbering it sequentially as part of the proof. even though it's kind of a subproof on its own. Let's see, what's the longest proof I've ever done stepwise? Not terribly long, except maybe my life, whatever that's proving. I'm still working on it. Not terribly long, I don't know, 20, 30 steps maybe. But you can buy one of the longest known proofs on Amazon. It's actually a 2-volume set. It's thousands of pages, and it's a proof of one theorem. And it's fascinating. It's what got me back into mathematics back in the 80s. Yeah, it's proof of the classification of finite simple groups, and it's a masterpiece of mathematics that we do not understand today, but it's tied into some kind of fundamental truths about the universe. Yeah, I'll have you do that on your midterm for, like, 2 bonus points or something. All right, where do we go from here? We're just about done. We've just showed that a plus b is even. What can we say in step 6? Seeing some talk around it. A plus b is not odd. And it doesn't hurt to put in this step 6, but it's a little, getting kind of pedantic about it. But since we've shown a plus b is even, we know that a plus b is not odd. In other words, we've negated the fact that a plus b is odd. And now we've done a beautiful job of what we can do in step 7. Right, step 7, we've proven a plus b is odd, and we've proven not a plus b is odd. That's a contradiction. I don't usually number the contradiction. But we've got a contradiction between propositions 1 and 6. So we have proven false. Well, go ahead.
So if that's false, then, wait, so I don't understand if,
Yeah. we assumed this, and this let us prove false. Well, you can't prove false. Right? Since we can't prove false, this must itself be false.
oh,
And so therefore, A is odd or B is odd.
oh, I see.
And really what happened was so let me name this. So let H be the proposition A plus B is odd. Let C, the conclusion, be the proposition A is odd or B is odd. Alright, so we started off, we stated H, and then we stated not C. And we did that as an assumption, and we argued, and eventually we proved false. So by assuming not C, we were able to prove false. So what have we actually proven? We've proven that not C implies false. That's really what this is a proof of. This is a proof that the negation of the conclusion implies false. And this is logically equivalent to the contrapositive, which is the negation of false implies the negation of C, which is logically equivalent to true implies C. And we know that true is true, and therefore, through direct reasoning, we can conclude C is true. So that's why an indirect proof actually proves the conclusion. But usually when we're doing this, we just kind of think, let's assume that the conclusion is false, and let's show that that leads to an absurdity, and therefore the conclusion must have been true. But that's what's actually going on underneath. So it's a direct proof of this. The other way to think about that is we're trying to prove C, which means we're trying to prove that, true implies C, which means we're trying to prove anything that's equivalent to this, including that the negation of C implies the negation of true, which is the equivalent of the negation of C implies false. So to prove C, all we have to prove is that if we negate C, we end up with false being true. We knew true is true, yeah. This is goofy stuff to try to talk about in a spoken language, which is why we have, propositional calculus to write this stuff. All right, so that's an example where an indirect proof really works nicely. And, all of the explanation and wordiness aside, it's a pretty quick proof. And we can use this for all kinds of things. And most of these even-odd problems, good chance that either a direct or indirect proof will fall out pretty quickly, and the other kind of proof might take a long time, or maybe not be doable. All right, other questions on this?
Can one use a proof? Oh wait, never mind.
Okay.
So you said for it to be provable, is it just not provable by our level of proof, or is there a proof that just straight up is not provable?
I think about it sometimes, and I was actually thinking about it last night, and I think you can find direct proofs for some of these things, but you end up either arguing cases or something like that. Like a direct proof that, where's the thing we were trying to prove? A direct proof that if A plus B is odd, then A is odd or B is odd. I don't know. I shouldn't say it's not doable. I suspect it is. A plus B equals 2n plus 1 equals, so I think you can write, n as two things. So this is 2x plus y plus 1 equals 2x plus 2y plus 1. And I think we can write A as 2 times j plus some constant, where this is either 0 or 1, and B is 2 times some other constant, where this is 0 or 1, and then try to force this sum to look like that. And I think you can get there, although I'm not convinced that we're not cheating somewhere along the way. But I don't think it's something weird like there's no way to prove this with a direct proof. I think that the direct proofs end up being more complex versions of the indirect proof. you end up basically, you know, assuming that that the sum is even, and then showing that something weird happens. But I don't know. I don't quite understand that at a intuitive level yet. But for working purposes, right, if you're trying to prove something and it's not feeling like a direct proof is getting you there, pretty quickly switch gears and think about an indirect and see if that might get you there. And a lot of times this pops out from trying to find a counterexample, right, or by exploring examples. So, prove that if A and B are odd, then A is odd or B is odd. So if I was trying to do this, I would probably start with some examples, right? So, you know, I'll pick two numbers that add up to an odd. Well, I don't know, 7 plus 6. And sure enough, yeah, one of those was odd. Well, what if I did 6 plus 6? Well, then I end up with an even number. What about, you know, 13 plus 17? Well, the sum's not odd. 13 plus 18, or 13 plus 16, or 12 plus 17, those will get me to odd. And I'll start realizing that, like, you know, I can wiggle around a little bit around the sum of two evens to get an even plus an odd that adds up, but that seems to be the only way my sum will come out to be an odd. And so you try to convince yourself that it's true, and then you try to find some way to break it. Some way to show that this, you know, isn't always a true statement. And whichever one of those, you know, lights the spark, that kind of tells you if you're looking at a direct or an indirect approach. If I keep, you know, finding things that make this true, then I'm probably looking at a direct proof. If I try to break it and I keep finding reasons why I can't break it, right, why that can't happen, then I'm probably working towards an indirect route. And it's you know, it's tied into the nature of thought and problem solving and logic and how we actually do that. And I think that's still a somewhat mysterious process. Are all odd numbers also prime numbers? No, definitely not. 9, for example, is not prime, but it's odd. But almost all prime numbers are odd, the exception being 2. Yep, someone got it in chat. Are there twice as many numbers that equal even if even plus even is even and odd plus odd is even? Ah, interesting. Well, except that even plus odd and odd plus even give you odds. So we've kind of got two ways to get odd numbers too. So if you restrict your attention to a set of integers like 0 to 10, I think you end up with the same number. So they're both equally likely, yeah. But then even if you go to the infinite set of all integers, we still we find that there's a countable number of each, and then we're back to cardinality. All right, let's talk about fractions. So fractions are interesting. When we first start, you know, looking at the world around us, so, you know, back before we knew how to make fire, maybe, at some point we developed the notion of counting, right? 1 rock, 2 rocks, 3 rocks, which are, you know, whole numbers and the so-called natural numbers, integers. And at some point we discover the concept of negative numbers and the concept of 0. And we start to model our world with, you know, whole numbers. But at some point we start to just think about ratios of numbers. and we find ourselves wanting to write things like, 1/2 or 2/3, or even bizarre stuff like, -5/17. But ratios of numbers. And so these are elements of the set of rational numbers. So the set of all I over j, where a and j are integers, and j is not equal to 0. That's the set of rational numbers. Rational, like, well-behaved, understandable, I don't know. And the Greeks, worshipped numbers. Pythagoras had a cult, and the people in this cult, would meet, and they would have rituals, I suppose, and such, and they literally worshipped numbers, right? They saw them as holy entities, pathways to truth and understanding, perhaps to the gods, and it was cult-like, and it was secretive, and they believed that, by understanding numbers and fractions, they could understand the entire universe. And this was good for a while. The set of all real numbers includes the rationals. This is true, but not the other way around. So numbers were worshipped, ratios of numbers were worshipped, and the belief was that, this was a sufficient set of things to understand and calculate everything in the universe. And Pythagoras and his disciples, being clever people, eventually made themselves a problem, which was, they studied geometric shapes, and here's a really simple geometric shape. It's a square, and each side has a length of 1. Yeah, you can see where I'm going with this. And we can connect opposite corners and form a diagonal. And we can ask, well, what's the length of that diagonal? It's one of the simplest things you can draw. Just a square and run a line from corner to corner. If the square sides have a length of 1, how long is that diagonal? Well, they measured it, and it was like, 1.414 something. And they wanted to know, well, what's the exact value? What's the exact ratio? Is it 141 over 100? No, it's a little more than that. It's a little less than 142 over 100. And they started looking for the pair of integers whose ratio described this length. And they couldn't figure it out, right? And so, you follow something and you try to find an example of it, and at some point, you start looking for a counterexample. Well, maybe there's not a fraction that represents this. And sure enough, eventually they were able to prove that there's no ratio of integers describing the length of this diagonal. In other words, they proved that the square root of 2 is not a rational number. And that was a bummer, because, whole numbers weren't enough to describe even something as simple as this, a drawing in the sand, and we can't describe the length with integers or ratios of integers. When they discovered this, yeah, their world was shattered. Did they publish it? No. They swore everybody to secrecy. Right? Because this is a big monkey wrench, And so they vowed not to talk about this outside of their little group. And one of the members actually went and started talking to people about this. He was an older man. I think he was in his 90s. And they actually took him out on a boat and pushed him into the water. For telling people that the square root of 2 is irrational. So this was harsh stuff. He actually survived. He swam back to shore somehow and survived. Yes, they broke rule number 2. All right, so So let's prove this. Yeah, well, this was serious business, you know. This would be like, you know, discovering um, that the world is flat, you know, or discovering that the sun really does revolve around the Earth. It would really shatter like some fundamental things, and you know, today I think we would publish that information just because, you know, we've got Twitter and someone would tweet it. But you know, 100 years ago, 1,000 years ago, different story. Um, and you know, Copernicus, when he came up with an experiment that showed that, you know, it's not possible that the sun is rotating around the Earth, um, that didn't generate as much concern as we think, right? Most people didn't accept his proof because he was using something totally different called the scientific method, and his approach was unconventional at the time, and so people didn't really pay too much attention to that. Although the suggestion that, you know, the Earth was not the center of the universe got him in trouble with the authorities. Um, but yeah, this was shocking. So let's prove this. All right. Um, you can go to jail if you release a prime number used for internet authentication if you know it. Really? I didn't know that one. Um, yeah, when we talk about crypto in a few weeks, probably next week, we'll go through the PGP algorithm for public key encryption, and there's some interesting backstory to that as far as government secrecy versus scientific discovery. Yeah, we're gonna spend a few days talking about crypto, and we will go through PGP, or sorry, RSA. Um, all right, so let's prove square root of 2 is not a rational number. All right, we got 10 minutes. We can do this, and then watch out for like angry Greek cult members who want to take you out for boat rides. All right, so let's do an indirect proof. So let's suppose square root of 2 is equal to a over b, where a and b are integers. Okay, and this is just our assumption. And we're going to argue to an absurdity. Now, I'm going to make one other assumption here. I'm writing the square root of 2 as a ratio of two integers, where it's equal to a over b. A and b have no common factors. So a over b is in simplest form. So, you know, grade school, we learn how to simplify fractions. If you get 15 tenths, you simplify that to 3 over 2. And you know that's simplest form because 3 and 2 don't have any common factors. But if you take 15 tenths and you simplify that to 6 over 4, you can simplify it again to 3 over 2. So we're going to write square root of 2 as a ratio of two integers where it's in simplest form. And we're going to argue to a contradiction. And it's pretty short, but I still don't know how someone came up with this originally, except maybe by wild trial and error. Alright, so square root of 2 is a over b. Let's square both sides. 2 equals a squared over b squared. That's algebra. 2 times b squared equals a squared. That's algebra. A squared is even, because it's twice an integer. B is an integer, so b squared is an integer. Alright, we haven't proven yet, but I'll be giving you homework next week where you prove that if the square of something is even, then that original number is also even. And that kind of makes sense, right? If you take an odd and square it, you get an odd. If you take an even and square it, you get an even. And so if a square is even, the thing you squared must have been even. If a square is odd, the thing you squared must have been odd. So I'll have you prove that for homework next week. But since a squared is even, a is even. And my reason would be, you know, future self proves this.
How do we know a squared is even?
Say again?
How do we know a squared is even?
Because a squared is twice b squared. And b is an integer, so b squared is an integer. Alright, well if a is even, we can write a as 2 times k, where k is an integer. Which means a squared is equal to 4 times k squared. But we also know that a squared is equal to 2b squared. And so 4k squared is equal to 2b squared. And so if we take both of these and we divide by 2, we find that 2 times k squared is equal to b squared. Which tells us that b squared, since it's twice an integer, b squared is even. Therefore, b is also even. Well, we've just argued to a contradiction because we've just shown that a and b are both even, which means they have a common factor of 2. In other words, a is equal to 2 times m, and b is equal to 2 times n, and so a over b is equal to 2m over 2n, which means we could write it as m over n, which is a simpler form than the original a over b. And that contradicts our original assumption. Therefore, the square root of 2 is not a rational number. And that's the end of our proof. And I'll admit, at least for me, this doesn't feel warm and fuzzy, right? When I first looked at this proof, I didn't see this coming. But reading through the proof, you know, I believe that, okay, I believe that, okay, I believe that. You've got to believe every step along the way until you get to the end and say, okay, well, I believe square root of 2 is not a rational number. But it didn't leave me with, like, you know, some sort of aha, I see what's happening, right? It's just a series of steps that take you. It's like following Google Maps to get to a destination. Doesn't mean that you understand where you are, you know, conceptually in the city that you're in. Yeah, so it's not mind-blowing. It's just, you know, got no choice but to accept the conclusion because we got there logically.
I'm going to talk about irrationals times rationals, like e to the I pi, and how that works out, or not in this course.
Oh, e to the I pi is interesting. Yeah, so there's this cool fact. E to the I pi is -1. I had a student with that tattooed on his arm one year. I thought that was really cool. You know, square root of -1, circles, growth rates, -1, they're all related. I don't know why. I don't think anybody does. But this comes out of something called Euler's formula. If you look at Euler's expression for sines and cosines in terms of complex numbers, this pops out immediately. If you were an electrical engineering student instead of CS, you would actually be doing this in these odds classes because you learn something called phasor notation, and it's an application of Euler's theorem to KVL, KCL, and this pops out and it makes your life wonderful. Yeah, they would have loved this in Pythagoreas' group. Rational numbers are interesting, though. The other thing that's cool about rational numbers is they've got the same cardinality as integers, right? There's the same number of rationals as there are whole numbers. But then, as we said that first Friday, when you jump from the rationals to the set of all real numbers, including, you know, square root of 2, you get to somehow fundamentally bigger group. And yeah, pi is definitely not rational. Pi is actually worse than square root of 2. It's what's called transcendental. There's no algebraic equation whose solution is pi. There's a simple algebraic equation whose solution is square root of 2. It's just this. So even though square root of 2 isn't rational, we can write it really simply as the solution of this modest equation. It's the number whose square minus 2 gives you 0. There's no equation like that for pi. That's what makes it transcendental. So this is all good stuff. These are great rabbit holes if you want to do some digging around on Wikipedia or whatever. Look up Euler's formula, look up rationals, irrationals, transcendentals, things like that. We won't get into much deeper than we have, you know, just now. But I think that's a cool proof to have seen, right? It's a good fact to know. It's good to see that it doesn't take, you know, a lot of sophisticated mathematics. It's really, you know, multiplication, squares, and this one fact that you'll prove next week in homework, that if a square is even, then the number's even. And it's really just an even-odd argument. Does the value of pi get doubled if working base 8? I don't believe so. I mean, like, do the digits double? I don't think so. Although base 5, maybe in some sense, out to some point. Yeah, there's lots of weird stuff about pi. Like, do you find every possible sequence of integers somewhere in the pattern for pi? And I don't think that's unique about pi. How big of an infinity is pi? Well, big of infinities, we're usually talking about sets, like the set of rationals or the set of integers, and pi is usually just a single number. The number of digits is probably countable, so the number of digits in a decimal expansion of pi is probably the same cardinality as z. Oh, number file, first thing that popped up, proof that E is irrational. Cool. Yeah, if you haven't looked at this and if you're intrigued by any of this stuff, this is a really cool channel, number file. And it goes way deeper into all of this stuff. We're really just kind of touching on it here. Alright, so that's a good stopping point. And we're going to leave proofs and propositional logic for a little while. Okay, and Friday we're going to start talking about number theory. So we're going to be talking mainly about divisibility of integers. So what happens when one integer is a multiple of another, or when it's not. And we'll build up a theory of subsets of integers, which will take us to something called modular arithmetic. And modular arithmetic is a really powerful way to do a lot of computation. And a lot of things we do in computer science that would normally be very difficult to do because they involve large numbers, we can do those practically by working with smaller numbers in a modular system. So when we talk about like hashing in 222 and cryptography and things like that, that's all going to be a lot of good number theory stuff. All right, so we'll start from there on Friday. Keep working on your homework for this week. Bring questions to class on Friday. We can go through proof questions and so on. Have a good afternoon. It's raining again, so that's cool. And I will see you next time.